We've talked previously about integrating energy modelling into the design process, and I think the conceptual modelling is a really good example of this, where these tools allow you to integrate simulation into early stage design phases. So first, a few principles. What is an energy model? And this little diagram explains some of the principles. In its simplest forms, you need a set of inputs. So you need to provide information about the building. And this might be building geometry, massing, form, system type, operation schedules. So you need to provide information about what it is you're simulating. We then need a calculation engine. And this is you might find this a slightly odd concept, that typically the software that you are making this simulation in is an interface for a calculation engine. So, for example, we will be simulating energy analysis in Revit, but the actual calculation engine is not Revit. Revit actually uses Do2. And it's the same with all different software types, that they are all using an energy calculation engine which is not the actual software itself. So for example, another piece of software called IES uses the Apache engine. And really, Revit or IES is the kind of user interface. The actual calculation engine is really a number crunching piece of software that takes the inputs, performs various formulae, and calculates the results. But because we like a more kind of visual interface, we normally use that through a front-end interface like Revit, for example. And you then have results. Now, as I say, in the energy calculation engine, the results would be purely data. It would just be numbers. And I think as designers, we're not very good at just sort of looking at numbers. So again, you normally work through a piece of software that will interpret the data, and normally we prefer that in a more visual format, such as bar graphs, pie charts, for example. And that's exactly what Revit does. So, levels of modelling, elements and inputs. So these are the kind of things that you might think about in an energy model. We've got things like building shape, orientation, which is all important. What's the building function? Is it a school? Is it an office? Is it a warehouse? Because that will have a big impact on the energy consumption. Floor area is obviously important. How many floors have you got? And things like thermal zoning of floors. So within any building, you don't provide the same level of comfort to all spaces. So a lecture theatre, for example, would have a certain comfort parameter, whereas a storeroom would have a very different comfort parameter. So you can define those zones. Floor to floor height, floor to ceiling height, obviously important. Then if we move on to the envelope, things like window dimensions, sill height, window to wall ratio, the actual kind of performance of that glass can be relevant, the foundations can be relevant, sometimes the internal partitions are relevant in an energy model, thermal mass, infiltration, so air infiltrating the building from outside. These can all be relevant. Then if we move on to internal loads, anticipated building occupancy, so how many people do you expect to be in your building and what are they doing? Building occupants produce heat, so you're all producing about 100 watts of heat right now. I'm producing a bit more because I've been running around. But generally, you know, we produce heat, and that's important. Lighting, power, electric lights produce heat. Then Then things like daylighting, occupancy sensors may be relevant in a more detailed model. If you have daylight sensors, the lights will switch themselves on and off. Internal load schedules, anticipated occupancy, lighting, plug load, that's an American term, how much electricity are you drawing by plugging in devices, is obviously all relevant. And then moving on to HVAC, heating, ventilation, air conditioning equipment. What kind of a system have you got? How efficient is it? How does it work? So all kind of relevant inputs. Now, in this session where we're talking primarily about conceptual level modelling, we're really interested primarily with building shape, orientation, function, floor to floor, and then a little bit about the kind of window size. And you'll see when we get into the software, that's all we're kind of modelling at this stage. And that's really important to understand, because you want to be able to use these tools at early stage in the design process. If you leave it too late, if you leave it too much later, you've probably missed the opportunity to simulate and change your building design accordingly. So, currently available energy modelling software. Just a quick look. So these are some of the softwares that are available, and there are lots out there. Some of them you're probably familiar with. Ecotect, which is no longer supported. Vasari here, which we were using last year, but which has now gone, is no longer supported. IES, virtual environment, which is a big industry software, which we have got in the school. We'll introduce that to you later. And, you know, many others. And the second column is the calculation engine. So we talked about the fact that these softwares are only the interface. And if you look in this column, you can see how the different softwares are using different calculation engines. Then we talk about graphic interface. So do they have a kind of visual graphic interface? Most of the ones that we like to use as designers will do, but there are some which do not have a graphical interface, and you have to simply insert numbers into them. Do they provide graphic results? Some of them do, some of them don't. The ones that we want to use have a graphic output. Are they appropriate for early design stage? So this is really relevant. Some of this software it's very good software, but it's only appropriate for a very detailed building level design. And it's not kind of designed for early design phase decisions. Revit can do both, which is partly why we favour it at the moment. Code compliance. So can you use this software for your kind of building legislation in your country, the country that you're practicing in? Some software is there more as a design tool to help you. Some of it you can actually use to demonstrate compliance with building regulations, building standards. And it's a kind of a mix there. And finally, freeware. Do you have to pay for the software? Which, you know, is a big factor if you're in practice. Typically, you get what you pay for, and quite often the free software is probably not as easy to use, not as sophisticated, and the software that you pay for is often better developed, better software. Now, we have a slightly unusual situation here because Autodesk gives academic institutions free access to their software. We are actually using quite expensive software, which is the Autodesk suite, because we get it free. In practice, there's a cost to that, but even so, certainly in the UK, most practices are now using an Autodesk product. Okay. Key metric here, just to understand, energy use intensity, or EUI. This is the amount of energy that your building uses per square metre per year. And it's a really important metric because it's per square metre. It means you can compare different buildings of different sizes. So you're not looking at the total energy output, but you can make a comparison per square metre. It also allows you to use benchmarks to get a feel for what level of performance should your building have. And I've just put a few conversion factors in there because sometimes the BTU, the British Thermal Unit, which we've mentioned before, it does get used, but it's not a metric unit. The units that we use here are kilowatt hour per square metre, which is the kind of the typical metric unit. You might also see a megawatt hour, which is 1,000,000 watts, watt hours per square metre. So a kilowatt hour, just to understand that, is a unit of energy, and it's the amount of energy if you run a device at 1 kilowatt power for 1 hour. So energy is power times by time, and that's why we tend to use this kilowatt hour unit of energy. Okay, you'll see that when we start doing some simulation. So a few benchmarks. This document is on Mole, and it's called TM46 Energy Benchmarks, and it's released by CIBSE, as you can see here. CIBSE is the Chartered Institute of Building Services Engineers. So it's an institute that is very concerned with energy and building performance, and they've released this document, and in this document it gives you a number of energy use intensities that you should be aiming for in different building types. So have a look at that on Mole. You don't need to read it all, but just have a little flick through it. Start to get familiar with that. I have just extracted a few examples from TM46. So just a few examples here. An office environment, you would typically aim for 95 kilowatt hour per square metre per annum for electricity usage. For fossil thermal, in other words, your heating and hot water system, which normally is powered by gas in the UK, you're aiming for 120 kilowatt hour per square metre per annum. And in terms of carbon emissions, a kind of benchmark figure is 75 kilograms of CO2 per square metre per annum. So those are a few examples. And that's the similar figures for a school. I'm not going to read all of those out, but aiming slightly higher, aiming to perform better in terms of carbon dioxide. And to achieve a carbon dioxide figure, all that they are doing is applying a conversion factor. So they're taking, for example, a kilowatt hour of electricity will equate to 0.55 kilograms of CO2. Now those conversion factors do change depending on analysis of how carbon intensive those energy sources are, which is changing all the time, of course. Another reference which is on Mole for you, you can download it through this link, is an architect's guide to integrating energy modelling in the design process. This is produced by the American Institute of Architects, and I'd recommend that you have a look at this. Really good document talking about the principles of integrating energy modelling. So we're focusing more on the skills today, but this talks more about the kind of principles and the implications. And a few more references. These are some videos produced by Autodesk which are looking at conceptual energy analysis. So some of this we'll be covering in today's session, but these videos, obviously they have a little bit more time and they cover some of the aspects in a little bit more detail. So I'd recommend that if you find the time, have a look through these videos. I think they're only about, I think they're about 8 or 10 minutes each, so it's only going to take you an hour to look through those. But sometimes you might find there's just a few little techniques that you might find useful. Okay, so we're going to get into Revit now. And I'm going to open the site model, this one here, site model with Conceptual Cafe Building, Energy Conceptual 2016, which is on Mole. You can download this. I've updated it. It was a Revit 2014 file on Mole, but it's now a 2016 file. So let's just open that. Okay. So, what we've got now in this file bear with me a second. Sorry, I've got a bit of a graphic issue going on here. I think I'll have to I'm just going to restart Revit because I think this is just something to do with my graphics card on my computer, so bear with me. While that's opening, just to recap, today we've got 3 sessions. The first session is looking at conceptual energy modelling. The second session is looking at building level energy modelling. And the third session is a workshop where we're going to look a little bit more depth at some conceptual modelling techniques. Okay. Let's hope this is going to open properly now. If it doesn't work, I'll just have to probably stop Captivate. Okay, that looks all right. Right, just going to open a few windows here. I'm a bit nervous about docking this now in case it has that problem again. Okay, Windows Tile, ZA, Zoom All. Okay, so this is the sample file that you've got, and what you're looking at here is we've got our Arts Tower site, and it's the sample site file that you were given in the previous weeks. Again, I'm using the incomplete version here, and one of your tasks is to complete that model, so I'm not providing you that model. Okay, and what we've got here is 3 different options for our new building. So you kind of need to imagine now for your assignment that you're working in an office, you're a kind of sustainability consultant, or you're an architect with sustainability expertise, and these 3 options have been produced, and your role now is to kind of understand the energy implications of these different options, and then to perhaps try making some changes to perhaps improve the performance. Now I'm just going to I'll just maximize option B here. Okay, so there's our option B. Now we talked about the crop box in previous sessions, but just to recap on that, if I go to my properties of my view and deactivate, sorry, section box, deactivate section box here, then that's our actual model. So we've got a bit more context than I was showing in that cropped view. That is of course purely a graphical view, so it's not going to change any of the results. So I'm just going to undo that, Control Z, because I tend to prefer to work with these section box views because they just make things a bit neater. Okay, so there's our conceptual building. The workshop today is going to talk in more detail about how you actually go about making these conceptual buildings. But for now, you've been provided with these three options. Right. Okay, what I just want to introduce you to now is the design options. Now, let's say you want to pursue a number of options in a project. Now, in Revit, what you don't do is make duplicate Revit files. So you don't make a copy of your Revit file and call it option B, and then make another one and call it option C, because that's a very kind of messy way of working. It also goes against the principles of integrated BIM, because in a BIM environment you might be working with many other team members. So you can't have multiple Revit files. So that's just a kind of the wrong way of working. What you do in Revit is you work with design options. And within the single Revit file, you can have multiple options in the same place, which allows you to test those multiple options. So just to briefly show you those design options, if you go to the Manage tab here at the top and go over to Design Options, and that opens up a dialog box. Okay, now the principal way of working in Revit is that by default there's a primary option, and that primary option should be considered everything in the model which will not change. So for example, your site, your topography, any adjacent buildings will not change. So that becomes your primary option. At a more detailed stage of the design, you might be putting the whole building into that primary option, because you might just be considering options of, for example, roof shape or window configuration. Your options then, you can create new options sets over here, and you can create new options. So you can put those options into a kind of subfolder. If we just create a new option here, and we can rename it. So let's just call that option E. Okay, so we've created a new option there. And this is a really efficient way of working with multiple design options. So I'll just close that for now. Now, a few important things to consider with your design options. When you activate a window, okay, you see as I hover my mouse over, it will allow me to select many of these objects, but it's not letting me select the building. And that's because if we go back to the Manage tab, under the design options, the active design option is currently set as the main model. If I change that to option B, now the main model, the primary model, is greyed out, but I can select my building. And that's the way design options work. I think the best way for you to learn that is just to open this sample file and just have a little play with it. Okay, it can get a bit confusing when you're trying to edit things and it won't let you, and it's because you're in the wrong option. Now, just one other setting on design options to consider. If I use the shortcut VV for the visibility graphics, I'll just expand that a little bit. Along the top, we've got a number of tabs. If we go to the final one, which is design options, then we've got some more settings here for design options. Okay, and you've got some control here about which option you would see in that view. So I'm not going to change that now, but that you have got the capability here to change the visibility of the design options. Okay, but for now we'll leave that in option B. I'll leave it with option B as the active design option because that will allow me to make some changes. Okay. Right, next. Let's now have a look at some of the options of a conceptual building model. Right. Okay, so if we look at this building here, what we talked about in one of those earlier slides here, we've got a building with some floor levels. We've got a building which has a geometry. It's got a shape. There's an indication of window area. There's an indication of shading. But the important thing to understand is it's not a detailed building design. So I'm not suggesting that this building would have windows that look like this. They're purely indicative of a certain percentage area of glazing and a certain depth of shading, a building shape, a building height. So it's really important that you don't confuse this with, if you're familiar with SketchUp, this looks a bit like SketchUp, but it's not, this is not the place where you would start designing that building in detail. It needs to remain as a conceptual level building. Okay, you'll get into all sorts of problems if you start trying to model a building here. I'm just going to shut that lamp. Okay. Right, so let's start to have a look at the energy settings. We need to go to our Analyze tab across the top. Click on that, and depending on how big your screen is, the energy analysis tools are here. If you've got a bigger screen, you probably get a little bit more space there, but it doesn't really matter. If you hover over, we've got four tools there. We've got energy settings, we've got show energy model, we've got run energy simulation, and we've got results and compare. So quite a simple set of tools really, but they do have quite a high level of complexity once you get into them. And I'm going to start by looking at the energy settings. And it opens up a dialog box, and we'll talk through in some detail now all of these energy settings. These energy settings will apply to all the conceptual buildings, all the design options in your model. So you're not, for example, comparing a school with an office. All of your design options have to be the same building. So you would not be comparing a building here with a building all the way over there. You're comparing different designs for the same site, typically. Okay. Let's just go through these. First option, building type. So what's your building? We've got dormitory, dining, exercise, hotel, library, museum, school. Ours is a school or a university building, so we select that. It's quite important that, because what Revit will then do, it will assume a number of default values for that type of building. So it will As soon as you tell it it's a school or a university, the operating hours it will take will be sort of normal university hours. The occupancy levels, the sort of plug loads, the sort of energy consumption, the lighting levels, your thermal comfort parameters will all be set for that type of building. So it's great really because it means you don't need to know all of those settings. And because what we're interested here is comparing a few different options, we don't want to be investing hours and hours putting in the sort of level of detail like operating hours 8 in the morning through till 6 o'clock at night, thermal temperature levels for a lecture theatre set at 22 degrees, temperature levels for a storeroom 16 degrees. We want to get some fast results here, so we'll just let Revit put all of those parameters in for us. Okay, location. Now, we've already set the location, Sheffield, South Yorkshire, but if you've not done that yet, you can, by clicking on the little button at the right, you can go back into that internet mapping service, choose your location, choose your weather station, but we've already done that. But if you've not set it yet, you need to set that. Now, next one, ground plane. This one is quite important, and this one catches a few students out every year. You need to tell Revit where is your ground level in the model. Anything below that ground level, Revit will simulate that as a basement. Basements have different, obviously different window configurations, they have different thermal mass properties. So just make sure you get that right level. Now, I happen to know that in this model, when we were making the topography, making the site, that ground level is our level 10. You can obviously rename that to anything you want. You could rename that as ground level if you want. But if you get that wrong, the simulation will be setting the wrong rooms as basements. So, for example, if we set that level too high, some of the rooms within that building will be simulated as if they're basements. Okay. Export category. You have a choice of rooms or spaces here. This actually does not matter for conceptual analysis. So just leave it alone on rooms. We'll talk about it later when we look at building analysis. Export complexity. You've got simple with shading surfaces, complex with shading surfaces. I would suggest always leave the shading surfaces on. What Revit will then do is any conceptual mass or any element in the model, it will use as a shading surface. So if you have a building that's blocking out the sun, that will be incorporated into the simulation. Simple or complex, you can play about with that. It's really just about the sort of level of detail of the simulation. I normally find I leave it on simple, and that tends to work quite well. But you can try that yourself. Okay, include thermal properties. Again, that's more at a building level. We'll talk about that later. For now, we just leave that unchecked. Project phase. Well, we're not using project phases yet. In Revit, you have project phases where you can put parts of your design into new build, existing. At the moment, we've put everything in new construction, so you can leave that. Sliver space tolerance, 304.8 millimeters. That's a 1 foot. So in America, in the United States, they still work in feet and inches. We don't, luckily. So the reason it's that odd number is it's 12 inches, 1 foot. And you don't need to change it. What it actually is talking about, it's quite a useful parameter. What Revit will do with the sliver space tolerance is if you had any gaps in your model, if those gaps are smaller than this figure, which is about a foot, then Revit will, for the energy simulation, it will join the gaps. Okay? It's actually really useful because it means your model will normally work because it will close that gap. Even if you've not modelled the building quite perfectly, it will still work. Now, what you find with some other software, like IES for example, it demands a much more precise level of modelling. And what can be really frustrating is you model your building, you've left a little gap somewhere to the outside world, and the simulation won't work because it's assuming that that room extends into the outside world, and the software gets very confused. So generally, I just leave that alone at 304.8. It seems to work quite well. You wouldn't normally have gaps bigger than that, bigger than 300 millimeters, and it just means that normally your simulation works. And it's really frustrating when you model a building, you run an energy simulation, and it just won't work. Okay. If you do get into problems, you can look at making that figure larger. Okay, building envelope, you can leave that parameter alone. Use function parameter. You can identify exterior elements, but I would recommend you just leave it automatic. The analytical grid cell size, which again is a funny number, it's 3 feet. But again, we leave that alone. You don't need to mess with that. What that will do is then when Revit's analysing your building, it will analyse on a grid cell of about, 900 millimetres, which is a good enough grade. You don't need to go any more detailed than that. Okay. Analysis mode. We've got 3 options here. Use building elements, use conceptual masses, use conceptual masses and building elements. So, have you got a detailed building model? Have you got conceptual masses? Or do you want to use both? Now, for our purposes, we want to use conceptual masses. We've not got a detailed building model yet. So we set that to use conceptual masses. In Revit 2014, this setting was positioned in a different place. Analytical space resolution is set to 18 inches. You can leave that alone. Surface resolution is set to 12 inches again. I recommend you leave that alone. Core offset. This is something you might want to alter. So if I just come out of this dialog box, look at our building here, we've got a building core. So if you see that rectangle on the top of the building, that is a conceptual building core. So most buildings of any size, you have a core down the middle which has got stairs and lifts and riser ducts in it, and then you have accommodation round the outside. So the building we're in is a perfect example of that. And at conceptual level, we're not interested in designing those stairs or those lifts or the detail of that. We're just interested in saying, look, there is a core in the middle of this building. And in the simulation, we don't need the same level of thermal comfort for a core, for stairs, for lifts, for toilets, for storerooms. They don't need the same level of servicing. And we can set that, if I go back into those settings, we set that here with our core offset. So if I just drop that down now to 2000 and hit OK, you see that our core got much bigger. The core offset is the offset from the outside of the building. So if I mean that's a very odd building now. If I go back into that setting, let's put that back to 3000, and our core offsets to 3 meters from the edge of of the facade. Now, this option here, it's actually a very small building. It's quite a peculiar kind of shape, really, to have a sort of, was it 6-story high building, which is quite small in footprint. But that's what that option is for there, that you can just decide how big is your perimeter zone, how big is your core. Again, at a conceptual level. You're not interested in designing it yet. Come to that later. Okay, back into our settings. Divide perimeter zones. If I check that, click OK, what the model now does is it divides our building, our perimeter zones, into north, south, east and west. And if I hover over here and use Tab, I can now select individual parts of that building. I could select, so I'm clicking Tab here to tab through different parts. So I've selected a different part of the building there. And the two settings here, if we divide the perimeter zones, it will divide the building up north, south, east and west, which, as you can see for this building, because the building is not actually orientated on axis, you do end up with a slightly funny configuration where, for example, here the south part of the building, I'll just zoom in a bit there, is kind of split across a corner. So sometimes that's not helpful. If we go back into that setting and uncheck divide perimeter zones, then it doesn't make that division north, south, east and west. But you can still, by using Tab, you can still select the different faces of your building. Okay, we'll come back to that in a moment. Okay, conceptual constructions. Now, at this stage in the design, we're not interested in getting into a huge amount of detail about what the building is made of, but you might want to play around with the basic construction types. So under the conceptual constructions, if we look, for example, here, mass exterior wall, what's it made of? And you can change that from high insulation, typical cold climate insulation, typical mild climate insulation, to no insulation. So you've just got some very kind of basic settings there for what the building is made of, which at this stage is all you need. But you can go in there and just kind of make some definitions about your insulation levels, your glazing type. Okay. Right, next one. Target percentage glazing. How much glass have you got compared to the wall? So we've got that set at 60%. If I knock that back to 20%, click OK. Our glazing reduces. Now it's not reduced on these facades, that's because I'll show you that later. We've set that facade individually. I'll come back to that. If I just pan around here, all of our other facades have now reduced to 20% glazing. And again, don't worry about the kind of how those windows look, because it's not a design, it's conceptual. Obviously you wouldn't really design a building with long, thin windows like that, but you might design a building which has 20% glazing. I'm just going to knock that glazing back, put that back to 50% there. Okay. Target sill height. So where do you want your glazing to start? Above floor level. Glazing is shaded. So do you want some shading on that glazing? So you can, if we uncheck that, okay, then we lose our shading on those windows. Let's put that back on. Shading depth. So how deep are your shading devices? 800 millimeters I've got that set at. Target percentage skylights. So have you got skylights in the top of your building? I've not got any, so I've left that at 0. If you did, then you've got skylight width and depth, which you can change. Okay. Building operation schedule. I've got it left at default, and because Revit knows that this is a university building, it will find the appropriate operation schedule. If you want to change that, you've got options under here. So 24/7, 24/5, year-round school, worship. There are some more detailed settings for when that building is occupied. Okay. HVAC system. Now, we're not really terribly interested. We're not comparing different boiler configurations, different HVAC systems, because we're approaching this more as a kind of building designer. We're not a services engineer. You can choose different HVAC systems here, and I've put a link on Mole for you to have a look. There's a little bit of guidance about what these different systems mean, but my recommendation is that for comparison of different designs, just leave it alone and compare the same system in each of your design options. You can get really confused if you start comparing a building with a certain HVAC system against a building with a different HVAC system, and you get different results. But I'm not sure that it's very helpful to you as a designer, because our expertise is not about kind of boiler efficiencies and HVAC systems. So I normally recommend that you can just leave that alone. Outdoor air information. Again, this is about how much air are you getting from the outside into your building through natural ventilation. And you've got a few different settings there that you can play with. You can select more than one setting if you want. Revit will always take the greatest figure from there. It's set by default at 8 litres per second per person, which is a reasonable figure. And again, normally for comparison purposes, I'd recommend you just leave that unchanged. Okay.